Thanks for the introduction. Thanks for the opportunity to be here, both to you and Celia. So I always like presentations like this to a slightly broader audience because I get to remind myself about these technologies that we're building. The solutions they're going to make are really going to be profoundly impactful on a global scale. And if you look at the modalities that people are using to build these types of systems and towards these applications, one of the leading modalities is based on what people like to call atomic physics. And so the way that I think about it, the way maybe to present it for this audience, is that atomic physics is shooting lasers at atoms to engineer the quantumness inside them. And so Vexlum, as a laser company, I'm particularly excited about what we're doing because I think it's going to unlock a lot of solutions that people don't have. And to understand us, I think the best way that I like to do it is to think about the origin story of Vexlum. And it really comes from the pairing of a research collaboration of the laser and atomic physics, atomic clock, and quantum computing group at NIST, partnering in a collaboration with the semiconductor and laser group in Tampere, Finland, in the Optical Research Center, where after that collaboration, there was some of the world's best lasers made for magnesium at 280 nanometers. And 6 years later into that collaboration, this Vexlum was formed as a spin-out company in Tampere, Finland. We've grown organically over the past 6 years, and as Mark mentioned, we now have a Colorado office, which I'm leading as the first U.S. employee. So unlike many other companies, we're totally vertically integrated, where we do everything in-house for better or worse, and we've brought what we think is an innovative laser technology to the quantum research field. And so really the meat of it is that we are making optically pumped semiconductor lasers. Some people call them VXLs, some people call them optically pumped VXLs, some people call them OPSLs. But taking this technology that existed for a long, long time and applying it to quantum research. So you can see the semiconductor gain mirror on the bottom left of the photo that I have, or the diagram that I have there, which we make in-house, and then we use an optical laser to pump that, and we put a cavity mirror around that. And there's a whole bunch of laser physics and details I won't go into, but the result is that these lasers are very versatile. We can make the semiconductor material wherever we want to bake the cake. We can change the ingredients to hit whatever wavelength we want. They're high power. They're inherently have great beam quality, and they're inherently low noise and single mode. So by putting inner cavity elements, we can lock them to sub-hertz. Our partners have locked to sub-hertz clock transitions and done really cool things with these lasers. And so I'm coming back to this idea of quantum physics or atomic physics is just shooting lasers at your favorite atom. What I did is I really wanted to convey the power and the breadth of the various wavelengths that we can hit. So take whatever your favorite atom might be, whether it's strontium for building atomic clocks, or it's ytterbium for building trapped ion-based quantum computers. Just go down the chart and pick out whatever your favorite wavelength might be, and that those are the powers in the systems that we're delivering right now or are in production right now. One way I like to visualize this data is just by looking at the spectrum and looking at all the various systems that we've delivered. And so the tagline that we've told many customers is that we can deliver a watt of power across the entire laser spectrum at low noise, single mode, single frequency. And we firmly believe that and stand by it. Some of the lasers, some of the recipes that we're baking for the semiconductor gain medium are still being developed and still in development. So the powers at those wavelengths are lower, but as time goes on, as we refine those recipes, the lasers will get up to that bar that we've set for ourselves and what our customers really want to see. So coming back to the lasers, we offer two products, the silver box and the yellow box. So the silver box we call the Velo. It's a research grade system that many users have in many atomic physics labs around the world. And then the yellow box is what we call the VXL, and it's a more ruggedized, more modular, more OEM type product that we're just beginning to launch in 2024. We've shipped a few prototypes of the system to date, but we're taking orders, but it's not out in the wild totally yet. So one last thing I'll leave you with, coming back to the slide of the various powers at the various wavelengths, is the images at the top. I took them from a bunch of iPhone photos that we have and just threw them up on the top of the slide with no color correction, no filtering, no nothing. It really, to me, exemplifies the fact that we are making these high power lasers at all these various wavelengths. And I'm a graphical person, so I really like to see these types of photos. I don't want to be cut off by Mark, so I'll just end at the thank you slide. And luckily I made it through my presentation without having to rush too fast.